Hello! In this video, I'd like to present for you Matrix's paper, Solution to the Entscheidungsproblem, that is, the decision problem, through Numero-Logical methods from 1982. In 1928, Hilbert and Ackermann asked whether there was an algorithm for determining whether a particular statement was provable or not. The following question now arises as a fundamental problem. Is it possible to determine whether or not a given statement pertaining to a field of knowledge is a consequence of the axioms? The idea of translating mathematical statements into formal strings of symbols that could be reasoned about in mathematical ways was relatively new at the time, giving mathematicians hope that there might be a way of completely comprehending the concept of mathematical proof, and thus, in some sense, completely solving mathematics as a whole. The original Hilbert and Ackermann text actually focused on the question of whether a particular statement was universally valid. The Entscheidungsproblem is solved once we know a procedure that allows us to decide, by means of finitely many operations, whether a given logical expression is universally valid. Different statements are true or false of different structures. For instance, is x times y equal to y times x is true of some structures and false of others. And the statement is universally valid if it's true of all structures. Of course, the real sort of interesting problems of universal validity don't really look like is x times y equal to y times x, but rather, do all of the axioms of a ring imply that 0 times x equals 0? That is, if all of the axioms of a ring hold in our particular structure, then is it necessarily the case that 0 times x equals 0 in that structure? In 1930, Gödel published his proof of his completeness theorem, that anything that was universally valid was provable in Hilbert and Ackermann's proof system. That is, their proof system, and this has been shown of a number of other proof systems since, fully captured logical consequence. So the two questions were the same. When you look at the writings of Church and Turing on the decision problem, they talk about it in terms of provability. In 1936, Turing published the groundbreaking On Computable Numbers with an application to the Entscheidungsproblem, which introduced to the world the idea of a Turing machine and showed that there was no universal algorithm to the decision problem. In particular, the question of whether certain Turing machines could be proved to halt was beyond the capacity of Turing machines to determine. However, this doesn't rule out partial solutions to the decision problem. While mathematicians had to give up on the grand dream of a universal algorithm for solving any mathematical problem, it was still possible to come up with algorithms for deciding whether specific subclasses of formulas are true. In the case of Turing machines, it's usually easy to determine whether it halts or not, whether we can prove that it halts or not, just by running it and noting if it halts or loops back into a state it's already been in. It's actually pretty rare to find a Turing machine with a really difficult halting problem. In 1931, Gödel published the proof of his incompleteness theorem, that there were formulas that were true but unprovable about the natural numbers. That if we focus our attention down from what's true in all structures or what's true in all structures satisfying particular formulas to what's true of the natural numbers, the notion of proof no longer captures everything we might want it to. The key idea in Gödel's proof was to take Hilbert's insight about viewing mathematical statements and proofs as formal strings of symbols one step further and turn mathematical statements into numbers. The basic signs of the system P are now ordered in one-to-one correspondence with natural numbers as follows. 0 is represented by the number 1, the successor operation is represented by 3, negation is represented by 5, OR is represented by 7, for all is represented by 9, left parenthesis is represented by 11, and right parenthesis is represented by 13. Higher primes and their powers are used to represent various first and higher order variables respectively. Gödel continues, hence, To every finite series of basic signs, and so also to every formula, there corresponds one-to-one a finite series of natural numbers. So for instance, the formula expressing that x and y are equal, that is saying for all predicates A, so A is a predicate, which means that it's a second order variable. So this here is how we express for all second order objects A holds for x, or A does not hold for y. And we translate this character by character into the corresponding odd numbers. Because A is a second order variable, it's going to be 17, the next available prime number, and we're going to square it to indicate that it's a second order variable. And then x and y are 19 and 23, the next available primes raised to the first power. And again, this formula expresses that x and y are equal to each other. If there's no predicate that's true of one, that's not true of the other. Once we've translated a formula into a list of numbers, Gödel instructs us on how to combine those numbers together to produce what we now call the Gödel number of the formula. He tells us to turn each of the numbers into the exponent in a prime factorization of a very large number. So here we have 2 to the first number, 3 to the second number, 5 to the third number, and so on and so forth. And then we'll just take all of those primes raised to various powers and multiply them together to get a very large number, the Gödel number for our formula. Inspired by Gödel's work, Dr. Irving Matrix worked to establish a complete theory of the use of numbers to represent logical formulas called Numero-Logic. Unfortunately, he did not live to see his grand work published, dying at the age of 40 in a duel. In 1982, Irving Matrix's daughter Iva published posthumously her father's fairly substantial solution to the decision problem. Just like in Gödel's incompleteness theorem, the key idea of the proof is encoding a mathematical question as a sequence of numbers that can be manipulated arithmetically. For instance, suppose we had the question if the set of prime numbers is finite. We first translate this question to a list of numbers via a equals 1, b equals 2, c equals 3, etc., to give us something that looks like this. Unlike the system of numbering that Gödel used, we don't assign any numbers to symbols, we just skip them. We then put these numbers into a matrix and take the determinant. In the original paper, Matrix enters the numbers in row major order, so reading from left to right and then top to bottom. But because the determinant of the transpose of a matrix is the determinant of the original matrix, you can also enter the numbers in column major order, from top to bottom and then left to right. When working with matrices, it's more natural to enumerate the entries in column major order, since the columns of a matrix are the images of the basis elements under the matrix. So those are the things that we're really interested in. But it's more natural when writing them to write the entries of a matrix in row major order, from left to right and top to bottom. Again, it doesn't make a difference. As we can see, the determinant of this matrix is negative 13,497. So that means our answer is false. The set of prime numbers is not finite, it's infinite. In general, if the determinant is positive, the answer is true, and if the determinant is negative, the answer is false. And if the determinant is 0, well, then the question is beyond the ability of this technique to determine. Again, due to Turing's proof, we expect there to be questions that are beyond the power of any one particular algorithm to answer, but what's notable about this technique is how rarely this particular case occurs compared to other partial solutions of the decision problem. The other remarkable thing about this technique is that it can answer much more than just basic arithmetic questions, as long as the number of letters is a perfect square. For instance, we can ask it about the Fermat conjecture, more commonly known as Fermat's last theorem, and get 48,824, which is positive, giving us a definitive numerical proof of Fermat's last theorem. We can also apply this technique to resolve major open questions in mathematics. is twin prime conjecture true gives us negative 54,119. So alas, the twin prime conjecture is not true. Those of you who have seen my video on fractran might be curious, does Collat's conjecture hold? Which gives us negative 1,827,457. So, alas, the Collat's conjecture is also not true. But there is some good news. If we ask it if p equals np, we get 1,703, which is positive, so p does in fact equal np. Alas, there's no hope of directly extracting an algorithm for solving an NP-complete problem in polynomial time from matrix's proof, since it's hopelessly non-constructive. For those of you who are skeptical of matrix's procedure, please note that if we take the determinant of the corresponding matrix, we wind up getting 79,333. Thus, matrix's procedure is entirely reliable. Most of this video is actually true. Hilbert really did dream of a universal algorithm for solving all mathematical problems, and justifiably so. At the time, many logicians had discovered a number of partial solutions to the Entscheidungsproblem, subsets of formulas where it could be algorithmically determined whether the formula was true/provable. And the proof of Gödel's incompleteness theorem really does make use of the numerical coding I showed. That's really how Gödel numbering is defined, replacing each character in a logical statement with the corresponding number, and then encoding the sequence of numbers in the exponents of a prime factorization. The matrix result is entirely fictional, as is Dr. Irving Joshua Matrix himself, and I hope clearly not suited for determining the truth or falsehood of mathematical statements. I'd like you to actually take a moment to ponder why. Why is it clear that this matrix determinant technique isn't suited for determining mathematical truth? The philosophical study of how we can come to know things is called epistemology, and I hope to talk some more about epistemology in mathematics later on this year. But this video isn't about the Entscheidungsproblem or matrix determinants. I only bring up this example because I want to talk about another method of knowledge generation that uses a precise sequence of mathematical computations, is carried out by a computer, uses linear algebra, gives definitive seeming answers, and even gives seemingly correct answers in some circumstances, but nonetheless is not a dependable source for knowledge generation. That's right, we need to talk about grading. Feldman describes this cognitive fallacy in Grading for Equity. We believe that the math of our grading software purges our grades of any unfairness, cleanses our grades of the potential stains of subjectivity or bias, and shields them and us against criticism from students, caregivers, and administrators. The thing is, while the actual numerical computations don't introduce any inaccuracy, the raw data and the choice of computation to perform contain plenty of incorrectness that the numerical computations do not remove. Feldman mentions many ways in which the common choice of grading algorithm is mathematically inaccurate. The tool just doesn't have the right mathematical properties for what we use it for. But I want to focus on just one example that I think highlights the subtleties in our choice of mathematical tools, and that's the zero. In mathematics, we understand that only certain operations make sense for certain kinds of objects, and this extends to real-life measurements as well. For instance, it doesn't make sense to talk of doubling or halving a temperature in Fahrenheit or Celsius, since what this means depends on which scale we're using. In Fahrenheit, if you double the temperature at which water freezes, you get a brisk spring day, while in Celsius, nothing happens. It may seem on the surface like it makes sense to talk about doubling or halving a grade, particularly in the case where we're measuring the percentage of problems students get correct on a particular assessment, but that's not really what we're doing. When we're grading a quiz, just like grading an essay, we have ideas about what A, B, C, and D level work look like, and we've hopefully calibrated our assessments such that percentage of problems correct, if that is how we're grading them, is a close fit to that. And for scales like these, where doubling and halving don't make sense, it also doesn't make sense to talk about 0. 0 degrees Fahrenheit is different from 0 degrees Celsius. And a 0 out of 100 is different from a 0 on the 1 to 4 GPA scale. Here we see that a 0 on the 1 to 4 GPA scale corresponds to somewhere in the 50s out of 100, and a 0 out of 100 corresponds to a -5 on the GPA scale. Neither of these is the absolute zero. The choice of which to award missing work is arbitrary. And the difference is profound. A 0 out of 100 on an assignment is almost impossible for a student to recover from. But a 0 on the 1 to 4 GPA scale is actually not nearly as bad. Of course, this seems like a very strange conversation to have, since we're several layers deep in bad teaching practices. Yes, grading is bad for learning, and it's not even clear at all what exactly grades are supposed to be measuring, but since we have to assign grades, yes, giving out zeros is bad for learning, but if we're going to give out zeros, then we should give them out on a 0 to 4 scale instead of a 0 to 100 scale. But there is merit to these sorts of conversations. Grading for equity recognizes that even small changes are better than nothing, and offers small changes that we can make while we're working on making larger changes. Grading for equity also goes into more detail about alternatives to giving out zeros. One option is to offer retakes, which I talked about in last year's April Fool's video. So, thanks for watching. I hope this video got you thinking about the ways that grading can, despite using mathematical computations, still produce results that are unfair and inaccurate. Except, of course, in the case of classes I took, where I got an A. For exclusively the calculation of my grades in those classes, the calculation of grades gave us as profound objective truth as any pure math. Anyway, thanks for watching. Please leave any questions or comments you might have below, and be kind to each other.